Hello everyone, welcome to video lecture series on microcontrollers and applications. We are at lecture number 8. In this lecture, we will discuss logical instructions and bit manipulation instructions of 8051 microcontroller. In previous lecture, we discussed arithmetic instructions, where we discussed syntax of arithmetic instructions, working of arithmetic instructions, examples of arithmetic instructions, and applications of arithmetic instructions. Today lecture learning outcomes are you may be able to achieve use of logical instructions to perform bitwise operations in assembly language programming of 8051 microcontroller. You may be able to apply bit manipulation instructions to control hardware ports and flags of 8051 microcontroller. You may be able to write logical operations for masking, toggling, conditional control in programs of 8051 microcontroller. The first instruction under logical operations are logical AND. The syntax for this instruction is ANL A comma source. Here we need to write like this. L stands for here logical. AN stands for AND operation. Logical AND operation. Logical AND operation. And already we know that for all arithmetic and logical operations, A is the destination. And the source operand is any register or a memory location data or any immediate data. Any register data or memory location data or any 8-bit immediate data. This instruction performs bitwise logical AND operation between accumulator and source operand specified in the instruction, and the result is placed in the accumulator. The result is placed in A register. If you see here, it will perform bitwise AND operation between source and accumulator, and the result is placed in accumulator itself. Let us see one example. ANL A comma hash 12. Another example is ANL A comma B, ANL A comma 50, ANL A comma @RA. If you observe here, these are the examples. This is written in immediate addressing mode. Immediate addressing mode. This is written in register addressing mode. This is written as direct addressing mode. This is written in indirect addressing. Here, this we are specified source operand in different ways. In case of the here immediate data, register operand, memory location data, here also memory location data, but here indirect way. But the actual operation we will see with the help of one example here. You can see, let us consider A is having 1, 2, B is having 0F. The binary representation is 0001 and 0010 for 1, 2. And similarly 0F is 4 zeros and 4 ones. This is 0FH in binary form. Already we know that under truth table, whenever both inputs are equal to 1, then only output is equal to 1. If any one of the input is equal to 0, so we know the 0, 0 output is equal to 0, 0, 1 output is equal to 1, 1, 0 output is equal to 0. So that means if you observe here, any one of the input is equal to 0. Here, here, here. So you can see output is equal to 0. Only both inputs are equal to 1, then only output is equal to 1. So that means the output becomes here 1, 0, 0, 1, 1. Both inputs are 1, that's why it is equal to 1. So this is the output. If you observe the output of a result of this operation, A bit can be masked or reset by ANDing with 0. Suppose, for example, here you can see this is the bit, actual bit available in accumulator. We are ANDing with 0 here. Okay, when you are ANDing with 0, so what happens in the destination in the accumulator, the same position will be masked. That means reset. Masking is nothing but here reset. If you want to mask any bit within any register, okay, if you want to mask any bit, you need to perform AND operation with 0, logic 0. Okay, this is the application of ANL instruction, AND instruction in 8051 microcontroller. Then coming to logical R, ORL A comma source. The syntax is ORL A comma source. Here source may be register or memory location or any immediate data. Register data, memory location data or immediate number, bit number. This instruction performs bitwise logical OR operation between accumulator and source operand, and the result is placed in the accumulator itself. This is the operation. It will perform bitwise and operation OR operation between A and source. The result is stored in accumulator. These are the examples in different addressing modes. Okay, let us see one example here. A is having 1, 2, B is having 0, F, H. Then if you perform the OR operation, so the OR truth table is, you can see 0, 0, output 0, 0, 1, output 1, 1, 0, output 1, 1, 1, output 1. So by this observation, when both inputs are equal to 0, then only output is equal to 0. Any one of the input is equal to 1, output is equal to 1. So from this, the result will becomes, here you can see 1, output 1, 1, 1, output 1, 1, 0, 1, 1, 0, 1, 0, 1, 1. Here both inputs are equal to 0, output is 0. So that means this is the output. A register is having this. This is the value. And from the observation, from this example, you can observe that if any bit is ORed with logic 1, suppose this is the bit. If you perform OR operation with 1, you are getting output is equal to 1. Okay. If you want to make any bit in the accumulator is equal to 1, simply you need to perform OR operation with logic 1. So this is the application of OR instruction in 8051 microcontroller. A bit can be set to 1 by ORing with 1. This is the application. Okay. Next instruction is logical XOR instruction. The syntax is XRL A comma source. Here also the source is register data, memory location data, or any immediate 8-bit data. And the operation is here. This instruction performs bitwise logical exclusive OR operation between accumulator and corresponding source, and the result is placed in the accumulator. The XOR operation is simplified form is it will perform XOR operation between A register and corresponding source, and the result is stored in accumulator. The examples are XRL A comma #12, XRL A comma B, XRL A comma 50, XRL A comma @RA. So these are written in different addressing modes, and here I'm considering two examples here. In first example, I considered A is equal to 12, B is equal to 0F. In second example, I considered A is equal to 12, B is equal to 12. Okay. Then to perform the XOR operation, first we need to know the truth table. X, Y are the inputs, Z is the output. If both inputs are equal to 0, output is equal to 0. 0, 1, output is 1. 1, 0, output is equal to 1. 1, 1, output is 0. From this, we can conclude that whenever both inputs are different, then output will be 1. So from this, the output is here. We are computed the output here 1. But our main intention is here we need to find out the application of XOR instruction. If you observe this, okay, observe this bit. Here the bit is 0, A bit is 0, but here it is complemented. So that means when you want to complement any bit, you can perform XOR operation with logic 1. To complement any bit, to complement any bit, and you can also consider this one also. Consider this one also. By observing these two bit positions, by observing these two bit positions, and this one also, all these bit positions, here you can see, here 0 means its complement is coming. Here 1 means its complement is coming. When you are performing with XOR operation with logic 1, XOR operation with logic 1, you are getting complemented bit. So from this we can conclude that a bit can be complemented by XORing with logic 1. Similarly, a bit can be cleared by using XOR operation with same bit. If you see here, this one, we are performed XOR operation with the same bit. This is 1, this is 1. The output is equal to 1. And here also, same bit. This is the 0, this is also 0. If you perform XOR operation, output is equal to 0. So this instruction is having two applications. First application is a bit can be complemented by XORing with logic 1. And similarly, we can also clear any bit by performing XOR operation with same bit. We need to perform XOR operation with same bit. We can get the we can clear that bit. These are the two applications of XOR instruction. Next instruction is clear accumulator. So the syntax is CLR-A. This instruction clears the accumulator contents. So let us consider, suppose for example, A register is having some 22H before execution of CLR. Then when you execute this instruction, A register will clear to 0. That means the result after execution of always clear instruction is 0 only. And one more important thing, it is only performed on accumulator. Clear instruction is performed on accumulator. Suppose for example, in some applications, I need to clear some other register, just like port 0. Let us consider port 0 is having 44H, but I need to clear the contents of port 0. We cannot directly perform clear instruction on this port 0. So that means first you need to move the contents of port 0 to accumulator. First you need to move port 0 contents onto accumulator. Then you can perform clear operation, clear A. Now A will be cleared, then only you can move port 0 with A. So then in this way you can clear the accumulator content, sorry, any other register contents. Then suppose for example A is having 0, this instruction simply fills A register with 00H. So you can see here A is having 12. After clear A will become 0. complement accumulator. So this instruction simply complements the each bit of the accumulator. So in the result, let us consider here A is equal to complement of A. So let us consider if A is having 55H, after a complement A, the result will be AH. So here each bit is complemented 1 0 0 1 1 0 0 1 and so on. So in this way it will complement the each bit of the accumulator. Then swap, exchange nibbles of the accumulator. Swap instruction is used to swap the nibbles of the accumulator only. Swap A. Let us consider this instruction exchanges the lower and higher nibbles within the accumulator. So let's consider A is equal to 42. After swap A, the A will becomes 24. This is the operation of swap instruction. Then rotate right, RR. RR stands for rotate right. The syntax is RRA. This instruction rotates all bits in the accumulator right by 1 bit position. MSB, sorry, the bit 0, LSB of the accumulator is rotated into MSB. You can see the pictorial representation here, how the rotate instruction works. So the rotate instruction always moves, rotate right instruction moves MSBs towards LSBs. You can see this MSB is moved to P6 position, B6 is moved to B5 position and so on up to B1 is moved to B0. B0 means LSB and this LSB is moved to MSB. So in this way rotate right instruction will work. So let us take one example here. If A is having 42 and then we are executed RRA instruction, then what happens, you can see this LSB is moved to MSB and this one is moved here, 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 this one, and this one is moved here. So in this way, each bit is rotated right side. Next, rotate right through carry. This instruction syntax is RRCA. This instruction rotates the 8 bits in the accumulator right by 1 bit position. The SB is moved to carry and the carry is moved to MSB. Okay, so you can see here each MSB is moved to LSB side and the LSB is moved to carry. The LSB is moved to carry and the carry flag will be moved to MSB position. And let us consider one example here. Initially the carry is equal to 1 and A is having 42. Now you can see here first the carry is moved to MSB. Okay, and whatever the LSB is there, that is moved to carry and each bit is moved to right side now. Each bit is moved to right side like this. Okay, so in this way RRC will work in 8051 microcontroller. Next, rotate left. The syntax is RLA. This instruction rotates all bits in the accumulator left by 1 bit position. Bit 7 is MSB of the accumulator is rotated into bit 0, LSBs. Here you can see the LSBs are moved left side. That means towards the MSB side. That means B0 is moved to B1, B1 is moved to B2 and so on. B6 is moved to B7 or MSB, and the MSB will be moved to LSB. So here one example is there. A is having 42. So in this case, each bit is moved to left side. So here you can see this bit is moved here, this bit is moved here, this bit is moved here, and this one, and the MSB is moved to LSB. In this way, rotate left instruction is rotating the data, and RLC, rotate left through carry. The syntax is RLCA, rotates all bits in the accumulator left by 1 bit position. The MSB is moved to carry, and the carry bit is moved to LSB. Here you can see all LSBs are moved towards the MSB side, and the MSB is moved to carry. The MSB is moved to carry, and the carry will be moved to LSB. So here let us consider initially carry is equal to 1. A is having 42. So now you can see MSB is moved to carry here. Okay, that means the output actually it is 1. Now the MSB is moved here. The carry is equal to 0 now, and each bit is moved to left side. This is moved here, this is moved here, and so on. And this is moved here. This is already here. The carry flag will become here. So in this way, rotate left through carry will work in the 8051 microcontroller. Next, bit or Boolean manipulation instructions. Actually, first we need to know where the bits are available in the 8051 microcontroller. So let us see now. 8051 is having few registers are bit addressable. Few registers are bit addressable. In addition to this, the internal RAM locations 20H2, 2F locations. Here there are 128 bits are available. 128 bits. So these addresses are ranging from 00H to 7FH locations. 7FH bits. Okay, total 128 bits are available. So each bit within these locations are addressable. So that means the bit addresses are available within the range of 00H to 7FH. In addition, you can also use any register which is having a bit addressable. So let us consider PSW is a bit addressable, and port 0 register is a bit addressable, port 1 is a bit addressable, port 2 register, port 3 register, and TCON register. These are these few registers are bit addressable. So to manipulate these bits available within these locations, or these bits available within the bit addressable registers, we can manipulate with the help of bit or Boolean manipulation instructions. So how we can manipulate, we will see with the help of these instructions. Okay. So what are the instructions supported by 8051? We will discuss one by one. To manipulate these bits, whatever the bits I discussed just now, that bits how we can manipulate, we'll see one by one. Now you can see the first instruction is clear carry. Clear carry. The carry flag is available in PSW. If you want to clear the carry, just you need to execute CLR carry, clear bit carry. So that means carry flag will be reset to 0 after execution of this instruction. Similarly, set bit carry, SETB carry means the carry flag will be set to 1. Set bit C means carry flag will be set to 1. Complement carry. So the carry flag within the PSW will be complemented by 1. Suppose for example, if it is equal to 0 actually, but you are executed CPL C, complement carry means after execution of this instruction, carry flag will be set to 1. Why? Because it is complemented. 0 means 1. If it is 1, its complement is 0. So based on the carry flag, the inverted value will be available in carry. Next, clear bit. Bit means you can use any bit within the bit addressable register or bit addressable location. So let us consider I can write CLR 00H. Okay, this means in internal RAM location 20H is available. This 20H is having 8 bits like this. Okay, so this is the address of this bit is 00, 01, 02, 03, 04, 07, 05, 06 and 07. 20H location, this is the byte address, but individual bits are also having their own addresses. Let us consider here clear bit. Suppose for example, already it is having 1, but now I am executed this instruction clear 00H, then this will become 0. This then the 00H bit available in 20H location is equal to 0 here. Only this bit will be cleared to 0. And similarly, set bit means suppose for example, I need to already in 07 bit position of 20th location is 0, but I need to set this one. Then I need to execute set bit 07H. After execution of this instruction, in this location, MSB bit will be set to 1. That means 07 bit position set to 1. Similarly, complement CPL bit. So here also, suppose for example, I need to complement this bit position, 04 bit position. So let us consider here 1 is available. Then I am executed CPL 04H. Then what happens after execution of CPL 04H? 04 location will be complemented. 1 will be complemented to 0. So in this way, complement bit instruction will work. Then we are having ANL C comma bit. This instruction will performs AND operation between C carry flag and a bit specified within the instruction, and the result is saved in carry flag itself. So this is the operation of ANL C comma bit. Suppose let us consider carry is equal to 1 and corresponding bit is equal to 0. The carry will be equal to 0 here. Why? Because AND operation. When both inputs are equal to 1, then only output is equal to 0. Output is equal to 1. But in this case, this is 1 and this is 0, output is 0. Then ANL C comma bit bar. So the only difference between these two is, in this case, the result is stored in carry only. Carry is ANDed with bit inverse. Bit inverse means, suppose for example, if bit is equal to 0, first it is complemented. That means 1. This one and already one is available. Let us consider same one is available here. 1 and 1 means AND operation between 1 and 1 is equal to 1. So that means here output is equal to 1. So here this instruction performs the bit of logical AND operation between carry flag and bit specified in the instruction inverse of this bit, inverse of the bit specified in the instruction. And the result is saved in carry flag only. And the result is saved in carry flag only. Then next instruction is ORL, similar operation with ANL operation, only difference is R operation. Similarly here also bit and bit bar, carry and bit bar, move C bit. In this case, the bit specified within the instruction is copied to carry flag. Similarly, we are also having carry may be copied to corresponding bit. Suppose for example, if this example we'll consider. So let us consider I use this instruction. Move 00H comma carry C means the C value. Suppose C is having 1. This 1 is copied to this 0H location, 00H location. So that means already here it is 0 is available. Now it will become 1. So in this way, a bit manipulation instructions are working in 8051 microcontroller. Summary of today's lecture. In this session, we discussed following key points: syntax of logical instructions, working of logical instructions, examples of logical instructions, applications of logical instructions. Next class, we will discuss how the 8051 makes decisions and branches execution using conditional control transfer instructions. Today quote is logical instructions are the decision makers of embedded systems, unlocking the smart control with simple logic. Thank you.